Today's advanced functions lesson is a review of all of the methods for solving polynomial equations that we've talked about so far. Recap. Solve means to find the roots, to identify zeros, to state x-intercepts. So most of the questions are asking you this, and they all mean the same thing. Note that zeros, roots equals to zeros if the equation is made equal to 0. We'll talk more about that later. It's just technicality. Polynomial function in standard form looks like this, so don't be intimidated by it. This looks really difficult. But all it's saying is whatever, see this n power, whatever your highest degree is, so if this were degree 5, then this n, this would tell you that this coefficient corresponds to the degree 5. So if you, let's look down here. We've got negative 6x cubed, so the negative 6 would technically be the coefficient that goes with the with the third degree. So that's all this means. And then this is your constant term. So for this one down here, it would be a 24th. It's just telling you that everything goes down in powers. Whatever your highest power is here, that's an n, this one's going to be one less than that, and so on until you get down to the power of 2, then the power of 1, and then you have x, no power. So this is a standard form, and this is what this particular graph looks like. In factored form, the same graph looks like this, and we just write the factored form out like this with however many, whatever the degree is, or however many roots we have, we would put that number of sets of brackets in. The other form we have is the transformed form, which in grade 10 we might have called the vertex form. And so example of that is this quartic here. It's a power of 4. It's like a parabola, but it's more flattened out, but it's got a vertex that we get from these two, and it's got the a value and the k value that are very easy to read. So that's using transformations. So here are some strategies for finding where those graphs cross the x-axis. First, use the factor theorem. So if you can sub in a value and get 0, then it means you've got a factor. To get those numbers that we sub in, we use that positive minus p over q. P is a factor of the constant term, which is a naught, and q is a factor of the leading coefficient. Usually you're going to get one, a small one. You're not going to have to start with a fraction or a number like 18. So usually if you start with 1, -1, 2, -2, you'll find one pretty quickly. And it's just trial and error. So if you had a question like this that said factor this, it's a power of 3 here, we would start with the factor theorem. And in this case, f at -1 is a 0, so that means this is a factor. So what do you do after you find a factor using the factor theorem? You would use synthetic or long division once you have a factor. What happens there, once we divide these, is we will have a smaller degree to work with for our quotient. You may be able to use one of the other methods on. If not, you're going to divide again. If it's still like a power of 4 or power of 3, then you might have to use the factor theorem again. I think you have one like that in your homework. Remember that for synthetic division, you must have a linear factor. If there's a remainder, then the divisors will not necessarily indicate 0. So if you sub something in here and you don't get 0, that means that your divisor that you're using, and the question might give you one, give you a divisor, you're not going to find zeros that way. So this is just the above example again. Here's our factor right there. Here's our original question, goes in here, and then we would do the division. Notice I've got a 0 placeholder in that spot. Another strategy is if you're in factored form, it's pretty easy to find the x-intercepts. You just get them from the brackets. You just isolate each one of these little brackets to find where the zeros are. So that's the easiest one. If you're in that transformation form, it's also not too hard to isolate x because there's only one x here. We do the opposite of BEDMAS, and we did an example like that in that video on that day. You can also graph to find the zeros. This is approximate, so if you try the factor theorem and nothing works, you're trying different things, nothing works, you're just going to have to graph by hand or with technology. This is your best bet. If it's in standard form and it cannot be factored, then you would just be trying to draw a sketch. You've got your leading coefficient, you've got your degree, you've got some information, you can use the y-intercept, you just do kind of the best you can. Well, that's kind of a worst case scenario here. We hope that there are other strategies you can use. If it's a quadratic, you can use a quadratic formula to find the zeros. If you can't factor it, you can always use a quadratic formula, but it only works if it's a degree of 2. And the last one we're going to talk about is just plain old factoring to find the x-intercepts. So we're going to review this in a little bit, all the different types of factoring that we know from previous years in school. So let's review trinomial factoring. A trinomial doesn't have to look like this. We're used to seeing this quadratic, meaning a power of 2. It doesn't have to look like that. What does have to happen are, and I'll go over this in a bunch of examples here. Let me put the first one up. The blanks you see, they just indicate where coefficients or constants would be. I'm not going to put any numbers in here just to not confuse it. I want to focus on the variables. So the variables in the second term, that's this one, must be the square root or half of the variable the first. So this is y squared. That means this has to be y to the power of 1, and that's the one we're very used to seeing. The z's are the same. We've got a z to the power of 4, but then we've got half of that power here and then none of it here. Right? The third term doesn't have any variable. So what happens when we have two variables? Let's look at the x's first. There's an x squared. There's a single x, but then there's no x's here, so that matches the pattern. But since we have another letter here, we have to go in the opposite direction. This is a y squared. Going in this direction, that gives me a single y, and going in this direction, still I have no y's. So this I could factor as a regular trinomial with sum and product or a decomposition. Here's a bigger one. I've got a to the power of 6. I've got half of that a here, no a here. I've also got a b at the front. I've got b to the power of 10, b to the power of 5, no b's here. But I have more letters, so we're going to start at the other end. C to the power of 4, going this way, I've got half of that. Going this way, I've got no c's. Perfect. And then d squared, d to the power of 1, no d's. So that means I could factor this using my sum and product. Let's do some examples here. Does this fit the pattern? Got m to the power of 2, a single m, no m. Good. N to the power of 2, a single n, no n. Okay, so we can factor this using, if you used crisscross method or sum and product or decomposition, it doesn't matter, whichever one you used before. So I'm going to do decomposition here. Decomposition says I'm looking for two numbers that will multiply to give me these two, leading coefficient and constant multiplied together. Two numbers that will multiply to give me 6. And they also have to add or subtract to give me 5. So what are two numbers that do that? They are 2 and 3, both positive. So decomposition says I take this 5 and I'm going to break it down. I'm going to decompose it. Instead of writing it as a 5, I'm going to write it as a positive 2 and a positive 3. So we've been ignoring the variables up until now, but let's put them back in. The 5 is this is a 5mn, so these have to have mn on them, because if they don't, then they're not going to add up to 5mn again. So this 2mn and 3mn add up to 5mn, so I haven't changed anything. Now the rest of the question stays exactly the same. 2m squared, n squared, and at the end we had a plus 3. So the next step, now I have 4 terms, called quadnomial, but I have 4 terms. The next step I'm going to do is group them together into pairs. So I group the first 2 together, I leave a plus sign in between. I don't make the brackets touch in the middle because I'm not multiplying. And now I'm going to factor out the common factor in the first bracket. So the common factor in the first bracket is a 2mn. That leaves me with mn plus 1. And what's the common factor in the second bracket? It's just a 3. And of course that will leave me with the same thing inside the brackets. That's the whole point here. If your brackets match, which they do, it means you did it correctly. Those brackets, we write them once. They are common to, the brackets are common to these entire pieces here. So this is one chunk, this is another chunk. Those brackets are common factors now. So I'm going to take out that common factor of mn plus 1, write it here, mn plus 1. What's left when I factor that out is 2mn plus 3. So that is an example of trinomial factoring with a few variables. Let's do another one. Solve. The first question said factor, this one says solve. So I'm going to have to take it one step further. I'm going to have to go and find an answer when I'm done here. Solve. Let's see, does this fit our pattern of trinomial? Because we've got a power of 4 here. That's pretty high. Our degree is of 4. So this is a power of 4. This x is half of that, which is power 2, and I have no x here. Perfect. That means I can solve it using any of my trinomial factoring methods that I already have. No. Okay, so since I can factor it like a trinomial, this one's like an easy trinomial because the leading coefficient is a 1. It's an invisible 1, which means I don't have to go through all of decomposition here. I'm just going to do sum and product. So I'm looking for two numbers that have a product of just this number, -4, because the leading coefficient's a 1, so that doesn't make any difference when I multiply it on, and a sum of 3. So what two numbers multiply together to give you 4 and add together to give you 3? Hopefully you came up with a +4 and a -1. +4 and -1. So because this is an easy trinomial, I can put these two numbers here directly into brackets, and I can jump right to my answer, which is, it's got to be the square root of this term here. So x to the power of 2 plus 4, that's this one, and then my other bracket is x to the power of 2 minus 1. And then what I see here, there's a couple of ways of doing this. Because I still have powers of 2 in the brackets, can I factor them any further? X squared plus 4. No, I can't factor that any further. I'm tempted to because it looks like a difference of squares, but except for the difference part, that's an addition. This one's a difference of squares. So I can factor this a little bit further. So x squared plus 4, I'm just going to write that again. X squared plus 4, difference of squares. Remember what we do for that? We set up two brackets. One of them has a plus sign, one of them has a minus, doesn't matter which is which. The square root of the front term at the front, the square root of the back term at the back. So now I can finish the question. It says solve, so I'm going to solve. I'm going to start from the far end here. When I solve this bracket gives me x equals -1. This bracket gives me x equals 1. And what about the first bracket? Let's take a look here. What I'm looking for is when x squared plus 4 would equal 0. That's the solution that I'm looking for. Bring the 4 over. I have x squared equals -4. So that means I take the square root of both sides, and I'm left with x equals the square root of -4. So that's not giving us any real roots. So the solution that we have is x equals 1 and x equals -1. Part C, how many zeros are in this question? Okay, this has a power of 8, has a degree of 8, which means it could have 8 zeros. It could have 8 x-intercepts. So it's a even power, which means it looks like it's going to have the general kind of end behavior of a parabola. So you can have both ends up or both ends down. My leading coefficient is a 6. It's positive. That means my function is going to have both ends up. So it could be something like this, coming down, maybe having a few bumps in the road here along the way. I don't really know. Oh, that's not very good. But both ends are up. It opens up. Maybe my x-axis is going right through here, and I'm getting a couple of zeros. The way I've drawn it here, this gives me 1, 2, 3, 4, 5, 6 zeros. I don't know, maybe my x-axis is just up here through the top, and I've only got 2 zeros. So how many zeros? This is a hard one. Let's see, does it follow because the degree is so high, does it follow the above pattern of trinomial. Can I factor this like a trinomial? It's got 3 terms, so that makes it a trinomial, but can I factor it with the trinomial factoring methods we have? So we've got x to the power of 8, half of that is here, none of it is here. Perfect. So we're going to try factoring this with sum and product. It's a difficult trinomial because it has a 6 in front, so we're going to have to use decomposition. Numbers that multiply together to give me 12. Oops, 12. I need 2 numbers that will have a product of 12, and those numbers have to have a sum of 7. What 2 numbers have a product of 12 and a sum of 7? 3 and 4. 3 and 4. So decomposition. Remember, decomposition means you take the middle term and you decompose it, you break it down. So instead of 7x to the power of 4, I've got a 3x to the power of 4 and a 4x to the power of 4. And it doesn't matter which one. I could have switched these and done the 3 first and then the 4. It doesn't matter. And my constant didn't change and my leading term did not change. 6x to the power of 8. Okay, now we've got a group of 4 terms. So we're going to group them in pairs. These 2 go together, leave a plus sign in the middle. Now we take a greatest common factor out of each pair. The first pair, what I'm going to take out is a 3x to the power of 4. That leaves me with 2x to the power of 4 plus 1. The only factor I can take out of the second set of brackets is a 2. That leaves me with 2x to the power of 4 plus 1. What a coincidence, the brackets are exactly the same. So I bring out that common factor, that big bracket is a 2x to the power of 4 plus 1. That comes out of this term and leaves me with 3x to the power of 4. And it comes out of this term, which leaves me with plus 2. Okay. Once you get down to binomial factors like we have here and here, you don't have to keep trying to factor. You can just go right ahead now and isolate x. I can try to isolate x once I have a binomial, and I could have done that right here. Let me just show you what I could have done here. I could have taken that bracket of x squared minus 1, and instead of doing difference of squares, which is what I did, I could have taken that x squared minus 1 and just gone ahead and done x squared minus 1 equals 0, bring the 1 over, and then the square root gives me x equals plus or minus 1. So once you have a binomial, you don't really usually have to worry about factoring any further if you've got a constant term in that binomial. So let's just go to that step here. Looking at this bracket, the question said how many zeros? So we've got 2x to the power of 4 plus 1. We want to know when that is going to equal 0, how it's going to equal 0. I bring the 1 over. 2x to the power of 4 equals negative 1. Divide by 2. X to the power of 4 equals negative 1 over 2. Now I've got to take the 4th root of that, and since it's a negative, it's not going to give me any real roots. So this is yielding no real roots. Okay, let's look at the other side, the other bracket. 3x to the power of 4 plus 2, we set that equal to 0. 3x to the power of 4 plus 2 equals 0. Bring the 2 over. 3x to the power of 4 equals negative 2. Divide by 3. X to the power of 4 equals negative 2 over 3. Same problem. So we're going to get no roots here, no real roots here either. So the question says, how many roots are there? We have no zeros. No zeros. Which means our graph could have been this one here. Let me put a y-axis there and an x-axis here. So if that were our x-axis, we've got whatever craziness is going on with this degree of 8, but it's all above the x-axis, so we have no zeros. Or you could think of it even as a quadratic that kind of opens up like this, right? No zeros. Question. There's more than one way to find the x-intercepts. Explain. Okay, there are lots of ways. The two ways we're talking about here are just plain old factoring and the factor theorem. So let's talk about factoring first. Here's our question for factoring. This one has a greatest common factor of x squared. Factor that out. And then I look at what's in the brackets and I see that that's a trinomial. It matches a pattern we just talked about. So I factor that further and it looks like this. And that matches, those are difference of squares. So let's factor, the question says explain, right? So I don't actually have to go ahead and do all this. The question did say explain. So if I was explaining this, I would say I would use factoring. I would use greatest common factor, trinomial factoring, difference of squares to find the x-intercepts. So from this point, I can either continue to factor it, or like I said in the last slide, because this is a binomial factor with a single x in it, I could just go ahead and get the x-intercepts that way. But let's do difference of squares, x minus 4, x plus 4. The second term is also difference of squares, x minus 1, x plus 1. So again, the question just says explain. So this one, we would use all our different factoring methods to explain how to find the x-intercepts. So we have all kinds of x-intercepts here. This one gives us an x-intercept when x is 0. This one when x is 4, and so on. You guys know how to do all that. Let's go over to the factor theorem. The factor theorem. Note there's no constant value in the standard form of the function above. That means when we do the p over q, there's no p value. So we don't have a constant term here. So we're going to do the greatest common factor just like we did over here. We'll do that first. There's our original question. And there's the greatest common factor. So now we just look, so this is factor, this x squared is done. I don't have to worry about doing anything with it. What I'm looking at now is the trinomial that's in here. I'm not going to do this factoring again. I'm trying to show you a different method here. So looking at the factor theorem, looking at this trinomial, we want to list all the plus or minus p over q possibilities for 16. Again, the question says explain. We don't have to do it. I'll just do a little bit of work here. So this is our p here, and this is our q. Nice that our q is a 1. That means everything's going to be over a 1. So I'm going to have plus or minus 16. Those could be possible zeros. Working my way down in factors, I've got 8 is a factor of 16, 4, 2, and 1. Well, that's a lot of possible factors. So the first thing we would do is find one that works. Then, well, let me skip ahead to that. I will tell you one that works. You could work them all out here, but actually we'll skip that. Once we have one that works, you're going to have to, I want to point out before I go on here, once I have one that works, notice this is a power of 4. So when I divide anything, x minus whatever I get for a here, whenever I divide anything into x to the power of 4, I need 0 placeholders, so let me throw those in there. X cubed minus 17x squared, and I need a placeholder for this single x and 16. Once I do that, and I do all the division, I'm still going to have an x to the power of 3 up here. I'm going to have to do it all again. So this is definitely a longer method than the first method I went over with you for the same question. Because this one we did the factoring pretty quickly. Look at all the factors that we got. The only one we've got so far is this one here. So I know that because I already did this, I know that I can either use 1 or negative 1 here, or 4 or negative 4. Once I do that, I do all the division. I'm going to have an x cubed up here. And then I'm going to have to, whatever I have up here for my quotient, I'm going to have to do the factor theorem again on that one. So this one would take a long time for sure. So if you can factor it, you maybe want to for questions that you can't factor, you should do that first, because the division, as you know, can take a long time. Even if you do synthetic, which is faster, overall I think it'll still take more time if you're doing long division if something can be factored. We have one more question. This is all, remember, this is review. Nothing is new here today. Find the zeros and use them to sketch a possible graph. Okay, we've got a cubic. Its leading coefficient is a 1. So I know it's starting at the bottom left and it's going to be doing some stuff, but then it's going to be going up to infinity in the first quadrant. So I know the basic shape of it. Because it's a power of 3, it could have 3 zeros. It could cross 3 times. It's got a y-intercept of -5. But from this equation, that's all I can gather. The question wants me to know, though, to find the zeros. So what are we going to do? Think of all the stuff you learned today. What do you think looks best? I just told you that factoring is easiest if you can, but we can't factor this one. Even if we tried to group it in pairs, put these pairs together, put these pairs together, you're not going to get matching brackets. So if the equation is factorable, then one of these combinations must equal 0. So we're going to see first if it's even factorable. So going through these are all, we have a leading coefficient of 1, so we have all integers here, +1, -1, +5, -5. So I want you to work through those, press pause, and find one that works. All right, hopefully you got the -1 here to be your factor. All the other numbers you got, remember, as soon as you find one, stop. You don't need to keep going anymore. But any other numbers that you get, you can keep them because they might help us to graph it later. So now we set up our division. And remember, division. I'm going to do long division. You can do synthetic division if you want to. So if you want to do synthetic division, go right ahead. If you want to do long division, go ahead. I'm going to press pause, and in 1 second after I'm done pressing pause, you will see the full solution for long division. Okay, great. I got a remainder to be 0, which I was expecting, and that's what worked out. So what I've got is f of x is equal to, I'm going to write down the original cubic, x cubed plus 2x squared minus 4x minus 5. So I know that factor, so the first factor I got right here was x plus 1. And the quotient from that is x squared plus x minus 5. So take a look at what I have here. My trinomial. Is there anything that multiplies to -5 and adds to 1? No, there isn't. So, do you remember from my list of things you can do, going back to grade 10, we're going to use the quadratic formula because this is not factorable. So the quadratic formula, you put it over to the left, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So we're just putting in the part where I have this little yellow curly bracket there. So I want you to press pause, do the quadratic formula, and when you come back I'll have most of it written out. So there's the work for the quadratic formula. We're getting approximate answers here. X is approximately 1.8 and -2.8, I think is what I have here. Whoops, 2.8. So the question said, find the zeros and use them to sketch a possible graph. So I've got this 0 here of x equals -1, and then I got my 2 zeros from the quadratic formula here. So none of these are all straight throughs, none of these are duplicates, so we're not getting any bounces or anything like that. So we're going to just draw, I'm just going to draw a quick sketch here. I'll just put it on the side, some axes. So remember the question said sketch a possible graph. So a possible graph here, what we do know for sure is looking at our original function, our constant term, this is our y-intercept. We're going to have a y-intercept at -5. We're going to have a x-intercept for sure at -1. We got that from our factor theorem. And then from the quadratic formula, we got an x at about 1.8, an x-intercept at about 1.8, and we got another one at negative 2.8, maybe like that. So that's good enough. We also know that it is a cubic that is overall increasing, right? Starting low, ending high, but I don't know where the turning points are, so I'm just going to put a curve in like this, turn around here, come through the negative 5, turn back around again, and there's my third 0. So that is a possible sketch of f at x. That is f at x. That's the end of your review for what we have learned so far in how to solve polynomial functions.